This video is about modeling simple harmonic motion. As always, read through the textbook to take careful notes, but now consider the following highlights. We're going to recall or bring back into view some things we've already discussed, such as the graphs of sine and cosine, and that would be the parent functions. We did then also transform them by changing them, flipping them, stretching them, and so on. We just want to bring back for now these basic parent functions to remind ourselves. For y equals sine of x, you'll recall some of the basic characteristics. It goes to the origin, 0, 0, and then increases as you move to the right on the graph before then decreasing. And then it just starts cycling back through with one full period being 2 pi. Of course, there's an x-intercept in the middle of that as well. And then for the cosine function, y equals cosine of x, this one starts at the top of the hill at the point 0, 1, and then from there decreases downward, of course cycling back through in the same kind of way, except this one has the low point in the middle of the period, which is also 2 pi, and then 2 x-intercepts within that period, as discussed again previously. So you'll also recall that we did transformations on these basic functions, or we call them parent functions. And so you may want to actually review that topic, previous one, to get familiar with that if it seemed shaky then or still now, because we're really going to use a lot of the same stuff in this modeling harmonic motion. So now we'll use the following similar formulas to represent simple harmonic motion. Again, if you go back and review the topic on transformations, you'll notice some formulas that look very similar to this, but some of the letters or variables were different. So let's now just kind of point out that for harmonic motion, number one, we're only using sine and cosine, so that keeps things nice and simple. And then you'll recall that in the front of the function, when we did this before, we used a capital A. Now it's going to be a lowercase a. Okay, same kind of positioning in the function, but again, slightly different variable. Instead of a b, a capital B, which we used before, now we're using what looks like an English W. It's actually a Greek lowercase, it's called omega. And so that's the variable you're seeing now tucked inside the trig function input or argument first. And then in parentheses, t minus c. So in this case, the way it's noted, t would be your main variable, kind of like your x, your independent variable. It could be t or x. Sometimes they'll use t for time in a scenario. That's fine too. And then you'll have minus c, which we've seen before. That would be like a phase shift or some kind of translation or moving on the graph. And then lastly, a plus b. Again, we used a different letter there, but same kind of thing. You can shift a graph upward or downward. The whole point of modeling, which this topic involves, is to make math look like something in real life so that you can understand what's in real life better, because we understand the math, right? That's the idea of modeling generally, and this will apply, as we've seen here, from what we know about sine and cosine. A couple notes before we get into this. Amplitude is going to be the absolute value of A. Now that should not surprise you. In fact, that's pretty much exactly what it was before, except again now we're using a lowercase a instead of a capital A. The period, which we've also done before, is going to be 2 pi over omega. Now that seems a little different because again we were using the letter B instead of omega when we did this in the transformation topic. So it's the same formula, just a different letter because now it's being used as omega. And 2 pi is involved because that's the pure period for sine and cosine, and really those are the only trig functions we're working with here. So we were even more general when doing transformations because we also did tangent and other things, right? But for sine and cosine, just 2 pi is it. So 2 pi over omega is our period. And then something called frequency, which we didn't really deal with before. It's more of an application, again, in the real world modeling scenarios. This is actually, if you look carefully, simply the reciprocal of the period. It's going to be omega over 2 pi, which, yes, looks like the period except it's flipped upside down. So it's simply the reciprocal of that. All right, so with those formulas in mind, let's now try some examples. Suppose the given function models the displacement of an object moving in simple harmonic motion. All right, so as you read through the textbook, you'll find, plenty of examples mentioned about what this could actually represent. It could be, waves in the water, it could be electricity, it could be lots of things that occur in these periodic cyclical wave-like patterns in the real world, which is all over the place, actually. We want to do a couple things. So part A says find the amplitude, period, and frequency of the motion. Well, thankfully, we had formulas for that stuff directly above, so I think we'll be able to plug those in just fine. And then secondly, sketch the graph of the displacement of the object over one complete period. Well, that's actually a lot like we did before, except it's even less now because it's only one complete period. So what we're going to do here is take our function, which is given as y equals 2 sine of 3t. And we're going to use the formulas we just noted for identifying the amplitude, period, and frequency. So you can tell right away out front that there's this 2 value. So you could say your a value equals 2. And that's going to help us know the amplitude. In fact, the amplitude, which is the absolute value of a, so we'll call that the absolute value of 2. Of course, that's just 2. So the amplitude is 2. That takes care of part of what we wanted, right? The period is going to involve the formula we have above. So for the period of this, we're going to use the new variable that's in town. So now it's 2 pi over omega instead of the b value we were using before. Okay, not a big deal. Let's write this out then. It's going to be 2 pi over omega. But what was omega? Well, in this case, we have to kind of represent this in the same way. So this function is given as 2 sine of 3t. And you may say, well, I don't really see something in the same place of omega as it shows in the way these formulas were given above. Okay, true, that's because c doesn't even show up. C is just the phase shift here and there isn't one. So really that'd be like saying 3 times in parentheses t minus 0. That'd be a way to kind of force it to look like the formula where again c would be 0. But it's not necessary to write the 0 there, so that's why you might not see it. The whole point, though, is that you can tell from this now that the omega value is going to be the number in front of the parentheses containing the variable t. So in this case, omega is 3, which means our period is going to be 2 pi over 3. And of course, that's going to help us with the graphing. We've done that a while already, so we'll be using the period when we graph, but for now we're just noting it. And then thirdly, they wanted us to find the frequency, so no problem, because the frequency, as noted above, is simply 1 over the period. In other words, the reciprocal of the period. So that would just be, in this case, 3 over 2 pi. Okay, so they wanted us to find those things, and now we have them. That is, we know the amplitude is 2, the period is 2 pi over 3, and the frequency is 3 over 2 pi. So with those three things now identified, let's do part B, which said to sketch the graph of the displacement over one complete period. Okay, well, like we did before, except we usually did 2 periods, or often did, or sometimes did 2 periods. In this case, if you're only doing 1 period, you know what the period is, so just mark it down. I'm going to go somewhere to the right in this graph, which the axes will be marked accordingly. We're using the letter T here for the independent variable, so we'll use T for the typically x-axis, and you can use y for the vertical axis here. If the period is 2 pi over 3, then we're going to mark that just somewhere down the line so that we know where to stop. Where is this function going to, right? So there's our 1 full period. As you may recall when graphing, we then started cutting things in half. So we're going to do that with this one. If I find out what half of this period is, I'm just going to kind of eyeball a marking somewhere in the middle of it. You'll note that to cut something in half, which is really our full period cut in half, it's like multiplying it by 1/2. So really I'm taking 2 pi over 3 and I'm multiplying it by 1/2. Well, that would turn out to be just pi over 3. Or 2 pi over 6 if you want to do that and then reduce it, which means that's right in the middle of our 1 period cycle for this graph. So let's be clear that we're really just using the parent function for, in this case, sine, where our example gave us sine, so we'll use that one. It might help to go back and just remember some of the basic characteristics of this, one period of the basic sine graph, which is you have an x-intercept, or okay, we're using t, but same kind of thing, x-axis, right? You have an intercept at the origin, 0, 0. You have one in the middle of the period, and then you have one at the end of the period. And then halfway between those intercepts on the horizontal axis, you have your maximum or minimum, the peaks or the valleys, right? So let's go back down to what we're working on here and note the same kind of thing. We know one full period starts at the origin, so we have a solid t-intercept there, and then one at the end, which for us is 2 pi over 3. And what that means is we also have one in the middle, since that's what the parent function for sine demonstrated. X-intercept in the middle, so we got one there too. And then we know that since the graph starts going upward, we would find a maximum value halfway between those two places. So I'm going to kind of eyeball halfway between 0 and pi over 3 and just kind of mark, the max value up there with a solid point. And then halfway between the next two intercepts, we'll mark, just kind of eyeball halfway between there and mark the lower, or the minimum valley point. We know it's going to hit those, which means we know the graph looks exactly like the sine function that it would, hitting all of those points. If you want to mark the maximum and minimum locations, you can. Again, you're just cutting stuff in half. So pi over 3, which was the span of between the first two intercepts, if you cut that in half, you get pi over 6. And then, in other words, you're counting that pi over 6s. So it's 1 pi over 6, 2 pi over 6. Next would be 3 pi over 6. Well, 3 pi over 6 is really just pi over 2, so you could mark that as well. That's that place on the t-axis, which is where you have your minimum point. If the amplitude is 2, then that tells us how to mark the y-axis, right? So vertically speaking, this graph goes as high as 2 and then as low as -2, since the amplitude is identified as 2 coming from this function. Okay, so there we have it. We've identified these pieces and then used them to plot the one period of this function on the graph. Let's try another one of the similar type or same instructions but different function. So this one's given as y equals -0.25 cosine of, and then in parentheses after the cosine we see 1.5t minus pi over 3. Well, you may understand just by glancing at this one that there's a little bit more clutter to sift through. It still has the familiar pieces we know we might need, but let's take note of a couple things. So first of all, we're going to rewrite this because of what we see inside the parentheses after the cosine. Remember, we need to be able to identify what that omega value is. That is not obvious until, as you may recall, we have to factor out this coefficient of the t, this 1.5 number. So we're going to start, and we did this kind of thing when we did transformations before. You may want to go back and recall or review some of those things, those examples. Same thing now. So I'm going to rewrite this entire function as negative. In fact, I'm just going to use the fraction form of it. Instead of -0.25, I'll call it -1/4, or you could use the decimal, it doesn't really matter. And then cosine, and then I'm going to use a set of brackets, which I think we did again back in transformation days, just to stay organized so that I can factor out this 1.5 without any confusion. So I'm going to write the 1.5 and factor it out of a set of parentheses that would then be containing the t variable and whatever would have to come after it in order to preserve the original expression, yet now with this 1.5 factored out. So the question is, if I distribute this 1.5 into these parentheses, I have to get this original expression in the parentheses. It's not hard to do with the t, because 1.5 times t is 1.5t, so that's fine. But the question becomes, what would have to go after the t, so that when I distribute the 1.5 to it, I end up with pi over 3. Now, this might take a second to think through, or I want to show you a bit of a trick for it. So, first of all, it might be easier, since you're dealing with a fraction with the pi over 3, it might be easier to work with a fraction instead of the 1.5. So let's actually do that. We're going to call that 3 over 2, which is the same thing as 1.5, just because it's convenient to deal with a fraction. Then your question becomes, well, 3 over 2 times what will give us this negative pi over 3? And you can actually set up kind of like a little sideshow algebra problem to figure this out. So sometimes a little sideshow helps. I'm going to say this, 3 over 2 times, I don't know what, I'm going to call it x, equals, and then you could say, you could either use the negative or not. If I say negative pi over 3, that's kind of what we're going for, right? Or you can account for the negative when you figure out the value here. The whole point is, if I were to solve this equation for x, remember this equation isn't really part of my problem. I'm just trying to figure out what I should be putting in with the t to make this all work when I factor out the 3/2, right? So if you kind of solve this algebraically, you do so by multiplying by the reciprocal on both sides of this, just thinking in terms of algebra, and you would get x equals, then you'd have negative pi over 3 on the right side there, times the reciprocal of 3 over 2, which is of course 2 over 3, which means negative 2 pi over 9. And so that was probably not obvious the way we had written this out earlier. This little sideshow problem of using algebra to figure it out, I think, helps. So really what that means is I want negative 2 pi over 9 written after the t inside my function. Okay, so all said and done, we should be able to distribute this 3/2 into this expression and produce the original expression. And of course, with this fraction, it would involve reducing and things. You could double check it, but that should be what we need for this one. So now let's identify the things we need. We're looking for amplitude. Amplitude is the absolute value of a. Well, in this case, a was the negative 1/4, or negative 0.25, as it was originally given in decimal form. That's fine. That means the absolute value of it is just 1/4, or 0.25. So we have the amplitude. That's part of what we need. Let's see, what was the list again? We want the amplitude, the period, and the frequency. Okay, so our period formula, as we saw above, we can write out here. So the period is going to be 2 pi, that's the normal period for cosine, over omega, this new value we're using in this section now. So in this case, we have to understand what omega is, but that's why we did all the factoring. Because if you go up and look at these original forms here, omega is what's factored out in front of the parentheses that contain your main independent variable. Okay, so with that being omega, now that we've factored, we can identify, omega for us is this 3/2 value, or 1.5 as it was originally given. You could really use either form of that. Which means that if the period is 2 pi over omega, that means 2 pi over 3 over 2. But then you have to judo flip the fraction to multiply by the reciprocal. This would become 2 pi times 2/3, also known as 4 pi over 3 if reduced. So that's our period. And then, let's see, we got the amplitude as 1/4, trying to mark the things we're looking for here. We wanted amplitude, period, and frequency. Okay, so then as we saw above, the frequency, once you have the period, it's easy because it's just the reciprocal. The frequency is the reciprocal. The period, which we just got, is 4 pi over 3, so we'll call that 3 over 4 pi. Okay, and then those are the pieces they wanted in this problem, so we got them. Now let's actually plot one full period of it, just like we did before. So we'll mark our horizontal axis as t, the variable given, vertical axis as y. This one's now a cosine, so we'll be referring back to the parent function of cosine in a second, but let's mark out what one full period is by just kind of moving down the line and marking a spot. It would be 4 pi over 3. That's what we identified here as the period. It's always good to cut stuff in half, as we've been seeing for a while now with these graphs, so I'm going to mark somewhere in the middle. Of course, we have 0 right at the origin there. Halfway between 0 and 4 pi over 3, well, they'd be like cutting 4 pi over 3 in half. which is the same thing as multiplying by 1 over 2, which is the same thing as just saying that's really 4, well, it's 4 pi over 6, or in other words, 2 pi over 3 for our halfway point. Now the question becomes, well, what is the halfway point, and how does it matter in this problem? Because we have a couple more things going on. You'll notice if we're dealing with cosine, the parent function for cosine up here. So remember, we started at the peak, at the top of the hill. When the t or x value is 0, you're at the top, and then it goes down, and then all the way ends at the top for one full period. So let's see if we can start marking this down. We're starting at the top at 0, so I'm going to mark a spot up there. And we know that it's going to end at the same place, so at the top as well, we hit at the end of the first period, another top of the hill, and then halfway between those, it's going to be the bottom of the hill, or the minimum value. Again, this is just keeping in with the pattern of the cosine function we saw. The x-intercepts are halfway between those places that we've now seen, right? So we could mark those or compute them without too much trouble. Let's go back down to our graph. Halfway between the markings we already have, we'll add some more, and I'm just cutting in half, so multiplying by 1/2. So 2 pi over 3, where we are in the middle, if I cut that in half, I'll have 2 pi over 6, which is also known as pi over 3. Just kind of marking some places down, right? And then halfway between these, let's see. If I start counting by pi over 3, there's 1 pi over 3, 2 pi over 3, 3 pi over 3, well, that's known as just pi. You could write it that way. And then 4 pi over 3. Okay, so things are kind of making sense in terms of our scale, and it actually should sound and look and feel very familiar to what we did when graphing these trig functions earlier in those previous topics. Now, what we're used to, or what we're expecting with the parent function, is to have x-intercepts at these middle places that we just marked, right? However, in this graph, or in this function as given, you'll notice there was also a phase shift. So to use the letters now familiar with this topic, this is the C. Actually, I think it was the same letter we used before, I think. So C is the value for phase shift given in these formulas, lowercase c. And that tells us how far we're going to be shifting over. We use the opposite of the sign we're seeing in it. So in this one, our c value is this 2 pi over 9. So let me mark this down here. So really, c is 2 pi over 9. And that matters because that's how we're going to be shifting this graph over. And as you may recall, use the opposite of what the sign is that you're seeing in front of it. So we see a minus 2 pi over 9, which means you're actually going to the right. Again, that's kind of a review topic from the graphing from earlier. So we're going 2 pi over 9 to the right. Well, that's kind of a mess because if you look at our graph, we don't have multiples of ninths on our marked on our axis. But we're actually not that far off because we have multiples of 3. So think of it this way. We have pi over 3 marked as our first place. If that were in terms of ninths, wouldn't that be 3 pi over 9, right? Reduced, that's just 1/3, 3/9. So for that reason, if I think that, or if I know that's 3 pi over 9, but I'm trying to shift everything to the right, 2 pi over 9, then I wouldn't be going quite that far, right? So we might kind of mark somewhere, not quite as far as that first x-intercept. That is the span we're trying to shift everything to the right. That is our 2 pi over 9. A little bit less than 3 pi over 9, which is, again, that first marking we had. So we're going to visually do that by dragging every point to the right that far. Now, I think it's helpful to use maybe a different color to help do this. So if I take this original point that was at 0, or at the top of the hill, I'm going to move it that far to the right, which is now directly above the 2 pi over 9 place. So we'll put a point there, and I'm just going to kind of eyeball the rest of these. So if I take the next point that was at pi over 3, right on the axis, move that over just as far. And then that's going to happen with every single one of our points. We're moving it over that exact same distance, the distance of 2 pi over 9, which visually I'm just marking down here so that we get an idea. Every point's moving over about that far. It's not necessary to go through and label, the fractional location of all these new places. You can, if that's helpful to kind of give you some stabilization in what you're drawing. That's totally fine to do. What you should be seeing, though, is the exact same one-period graph that you'd expect for a cosine in this case. Now, we haven't dealt with the amplitude yet, so we're going to deal with that soon, but hopefully you're getting the period and then the shifting down, which is stuff we've done before. Now, another important aspect of this function, as you'll recall if you go back and look at it, is that it had a negative sign out in front originally. Now, the amplitude takes the absolute value, which kind of negates that negative for the purpose of understanding the amplitude. So we got positive 1/4 for that. That's fine. However, to graph this thing, that negative does matter. So that means instead of starting at the top, the function would have actually been starting at the bottom. So there's actually a quick fix now. What we're going to do is go and find all of our peaks and valleys and simply reverse them. So the point that I had at the highest part here, which was the point, 2 pi over 9, comma, originally it would have been 1/4, if that's the amplitude. That's going to be reversed down negative now because of the fact that the original function had the opposite with it. So I'm going to do that and just relocate that one. You can do that either by what I'm doing now or by originally plotting the parent function for just negative cosine. I wrote the positive one because I started up high, but either way you can account for that. And then that will change the location of all the peaks and valleys. So the lowest point also shifts above, and we ended on a high point, but it's actually going to end up at a low point. Alright, so what we end up with is, again, something that looks exactly like the cosine function within one period, but it's shifted over and it's shrunk down. We should label our axes here. So like vertically speaking, we have 1/4 as the highest and negative 1/4 as the lowest, accounting for the amplitude there of 1/4. And so that's enough detail we would need for graphing this one by hand. Okay, our next example says find a function that models the simple harmonic motion having the given properties. I want to find a function, and it says assume that the displacement at time is 0 at time t equals 0. Now, what does that mean? Well, recall from our models above, you can go back and look at them, they're more pretty above, but you have two basic options. You have sine of t, or you have cosine of t. And if you look at the basic graphs of those parent functions, sine of t starts at the origin and then in a positive sense goes up, down, and then back to the axis for one full period. Cosine starts at the top, or the top of the hill, goes down and then back up to the top of the hill as well. So we've seen this plenty by now. But the point is this: if you assume that the displacement is 0 at time 0, there's only one of those that does that without doing some kind of phase shift and all that stuff. So let's keep our lives simple and point to the fact that, well, that's kind of where sine starts, so it's probably easiest just to use the sine function for this. Okay, with that being the case, let's now keep going. The amplitude is just given as 10 centimeters for this first one, which tells us, well, you could just say A equals 10. Right, now could A be negative 10 because we're using the absolute value? Well, sure, okay, but let's keep things as simple as possible. The amplitude is 10, that means A could be just 10. Now, if the period is 3 seconds, let's recall from above that we have a formula for period. We know that the period is equal to 2 pi over omega. And in either case, we're using sine here, so that's fine. If the period is 3 seconds, then what we can say is that 2 pi over omega equals 3. The whole point here is to be able to find what omega is from this. So if we take this equation, I can get rid of the p, we don't need that now, we know what p equals. It's 2 pi over omega, and if that's 3, We can solve for omega by just kind of using some algebra. If you multiply both sides by omega, then these omegas cancel and you get 2 pi on the left side equals 3 omega. We're trying to find out what omega is, right? If you divide by 3 on both sides next, those 3's cancel, and we're left with omega equals 2 pi over 3. Our whole goal here is to construct or put together this function that has these properties, right? Well, if you think about it, we have enough to do a very simple version of it. We can now say y equals, remember the first part is a, which is related to the amplitude. Well, we already said that could be 10, so we'll say 10. We're going to use a sine function because of where the origins, the intercept starts at the origin conveniently. And then we just found out that omega is 2 pi over 3. Well, we could put that in directly next. 2 pi over 3. And then we can plug our variable, and you can use t. I guess they don't really tell. Oh yeah, t for time, so we'll use t as well. So you could say y equals 10 sine of 2 pi over 3 t. And that would do it given the properties we have in our functions above and what they gave us for this one here. All right, let's do another one. The next one says the amplitude is 6 inches. The frequency is 5 over pi hertz. H to z is a hertz. This is just a metric used in physics and engineering. So we have this information. Let's recall again that we could plug in some basics here. We are in still the same scenario where the displacement is 0 at time equals 0. So we already said that sine is an easy one to use for that. We'll probably just stick with that. The amplitude is 6, so let's just assume A might be 6. The frequency is 5 over pi. Well, we have a formula for that one as well. Go back up to the ranch here where we had our formulas. There we go. Frequency was the reciprocal of the period, as you may recall. So it's omega over 2 pi. Okay, so that means for this one, omega over 2 pi will equal 5 over pi. Now, the whole point of giving us this information, kind of like they did in the first part, but except it was the period they gave us, is for us to be able to find omega so we can plug it into our function. So all we got to do now is solve for omega in this equation, kind of like we had to solve for omega in the previous one, except that was period. Now it's the frequency formula. So let's see, you could just multiply both sides by 2 pi. On this, that would give you omega alone on the left side equals, if I multiply the right side by 2 pi, I would end up with 10 times pi over pi, or just 10. So omega would be just 10 there. Just solving for omega algebraically. Remember, omega is the thing that looks like W. And if that's the case, that simply means omega is 10, which means we can put this stuff together now. So we could say y equals 6, that's our A value, times the sine of, and then it's omega t, which would be 10 t, since we found omega to be 10. And so there's our function. All right, let's go on to another example in these similar topics here. This one says the following: find a function that models simple harmonic motion having amplitude 60 feet and period 0.5 minutes, and then assume that the displacement is maximum at time t equals 0. What does that mean? If the displacement is maximum, think about the options we have and which one fits better with that. So if you go way back up to, I'll kind of mark this over here where we kind of redrew those parent ones. For cosine, it starts at the top of the hill. That would be maximum displacement for t equals 0. So again, as you may recall, you can do phase shifts and things to make sine and cosine basically look like each other with some adjustments or transformations. We want to keep things as simple as possible. If this one's maximum at time equals 0, let's use the parent basic function that already has that property, which would be cosine. So let's just say we're going to use cosine here out of that convenience. But otherwise, we know the amplitude is 60 feet. Let's let A equal 60. And if the period is 0.5 minutes, again, we have a formula for period. Period would be 2 pi over omega, but they're saying that that is 0.5 minutes. We'll call that 0.5 because all we got to do is solve for omega here. So use some algebra to get omega alone, try it out. You should end up with, if you flip both of these around, 4 pi for omega. So again, you're just kind of solving for omega using some simple algebra there. So omega is 4 pi. Why does it matter? Because that's part of what we need to put this function together. So let's do that. In fact, I think we're good now because we can say y equals a, which is 60, times the cosine, which we decided to use out of convenience for this one, of omega t. Well, we just found omega to be 4 pi, so we'll say 4 pi t. And that function could model exactly what we need. All right, let's try one more problem. This example is going to be a bit more wordy. This starts in the following way. It says, the Bay of Fundy in Nova Scotia has the highest tides in the world. In one 12-hour period, okay, that sounds important. In one 12-hour period, the water starts at the mean sea level, rises to 21 feet above sea level, above that mean sea level, drops to 21 feet below, then returns to the mean sea level. Okay, so assuming the motion of the tide is simple harmonic, find an equation, that's our goal, that describes the height of the tide above the mean sea level. Okay, sketch a graph that shows. All right, so let's start by just kind of maybe doing a rough sketch just to brainstorm what we have going on and what options we have. Notice what it says here. The water starts at the mean sea level. Now, what is that? Well, we're not exactly sure, but let's just call that 0 for a second. If it starts at 0, and then it rises to 21 feet above, so it goes 21, we'll call that 21, it goes to 21 feet above, drops to 21 feet below, so maybe there's a negative 21, drops down to that, and then returns to the mean sea level. Okay, so if you just kind of use those words or convert those words into a basic picture, we're looking at what might look like a sine of t function because of the fact that it starts at the origin and goes up and then so on. It just fits the pattern of the parent function for sine that we have drawn above. So it's just probably convenient to use that if we're trying to find an equation that describes this, right? Now, let's also note that it says this happens in a 12-hour period. Well, what we know about sine function then is that one full cycle, so starting, going up, and then down, and back to where it was, is 12 hours. Of course, that would mean, halfway in between is 6 hours, and so on. We don't need to mark every tick mark on this, because I think we'll be able to get what we need from this information. Given that we're starting it with a model that goes upward, as we've drawn, like a positive sine function, and that we know how high and how low the tide goes with the 21 above and 21 below, I think it's fair to say we might be able to just say A equals 21, right? A positive 21 would take us upward, which we've kind of used to model this. And so A could just be 21 for the amplitude, right? Now, beyond that, we don't know a whole lot about, well, they say the period is, one full cycle would be 12. So we could do this a couple different ways. You can use frequency or period with that information. You will see if you read through the book for the definition of frequency, they would say that frequency, just more as like a concept, frequency would be the number of cycles per hour or per time, whatever the time is, and this one it's hours. So you can use frequency or you can use period, right? We know that period, we have a formula for that. Actually, they're just reciprocals of each other, so you could use either one. In this case, they already tell you that it takes 12 hours for a full period for this tide to go up and then down and then back to where it was. So really, you could use the formula for each of those, but I think maybe from what we were doing earlier, period's more familiar. So I'm going to use that one What we know is the period formula is 2 pi over omega, and if that equals 12, we can simply solve for omega using algebra there. The frequency formula would simply be the reciprocal. You would use omega over 2 pi. Both will get you where you need to be able to solve for omega. So let me do this here. If I use algebra, okay, shortcut would be to switch these two values, which you can get by clearing the fractions and moving things around. So we'll get, take as many steps as you need to do this algebraically. Omega would be 2 pi over 12, which is also known as pi over 6. Okay, so if that's what omega is, then we can plug it in place with what we have so far. We can say y equals, we decided we're going to use sine, and that a should be 21. So fine, we'll call this 21 times the sine of omega t. Well, if omega is pi over 6, as we solved there a second ago, we can say pi over 6t. And that would be a function that could model this very scenario given the information.